Okay, so I've rigged up this little system here where I'm going to try working through the exam, and you all can listen and have some video of me working through these problems, and hopefully this will work as well for you as the lecture we usually take to review the exam results. Alright, so this is question number 1, and what we have is a DC generator, and it's directly connected to a DC motor. And part A says, for the DC motor, where, rotor or stator, must the armature reside? Very briefly explain why this must be the case. Okay, so it must be the rotor. And we know this because the rotor moves. And in a DC motor, the armature, well, in anything, the armature is where the power is being produced. So the DC motor takes as input electrical energy, and it has as output, right? So the produced power, okay, is mechanical motion, torque on the rotor. And you can't possibly have the stator because by definition the stator is stationary, so you're never going to get any mechanical energy out if you were to call the stator of the DC motor the armature. Okay, so the rotor moves and thus produces mechanical energy. Okay, mechanical energy being motion, and so we need that for what we're doing here. Okay, now as we move down, okay, we've got, to start with, the DC motor is whirring along happily at maximum speed. Is current through the armature windings at a minimum or a maximum? Why is this the case? Explain carefully. Okay, so if it's at its maximum speed, that's the key bit of information here, and we look at the relationship between counter voltage and velocity of the rotor and the magnetic field applied to the rotor. Okay, so V counter, remember this is from the generator effect, and the faster we spin a coil of wire in a magnetic field, like we're doing here with the DC motor, the more counter voltage, the more voltage, and thus more countering voltage, it will produce. So this is at max, so this is at max. And if that's the case, then if we look at the relationship for the net voltage across the armature, okay, so the thing that's going to tell us with Ohm's law how much current is going through the armature, that's equal to the source voltage, so V sub S, minus however much counter voltage we've got. All right? So we know that this is at a max, right? The countering voltage is at a max. And this is fixed. So the arm, so the net voltage across the armature, is going to be at a minimum, right? We're canceling out as much of the source voltage as we can with this maximum countering voltage at the maximum velocity, okay? Okay, so last link, if the net voltage across the armature is at a minimum, then the current through the armature, which according to Ohm's law is just this, right? So we've got net voltage across the armature, we've got resistance to the armature windings, and we've got current. And if this is at a minimum, then this must also be at a minimum. And there's our answer. Okay? So it's at a minimum here. Okay? Not a maximum. Okay. Last part of the question, and I guess this is running pretty long, so I'll probably chop this up, but we'll see how it works out. And let me see, get it all centered here on the video. So given that we don't see a rectifier in the circuit diagram for the DC generator, what device makes the output of the generator DC? Okay, no explanation necessary, so we just have to name the thing. There were two different things that gave us DC out of a generator. One is the rectifier, but we're not using that. So the only other thing that could be happening is that we're connecting the rotor of the generator to the circuit through a commutator, which touches some brushes. And remember, it flips the polarity of the voltage if you're just talking about a split ring, every half turn, and so you always stay on the positive side of voltage, and so you always get current in the same direction. Okay, but commutator, that's all you need for part C, just a point there. Now, relatedly realize we have a couple more parts to this question. Okay, so we've got this. So this is in reference to the little DC motor demo video that I put up before the exam. And if you took a look at that, then you might get the reference of me sticking a writing utensil into the fan. But in any case, you can figure out what's going on just based on the equations that we have that describe the behavior of DC motors here, okay? So I slow down, or some wacko slows down the rotor of the DC motor. And so we're going from maximum speed to a significantly lower speed. And what happens to the torque on the motor rotor? Okay, so what happens to the torque is that the torque increases. Okay, now why is that? Well, if we look again at those relationships, V counter proportional to V times B. So this is lower. So that means that the net voltage across the armature, okay, so if V is lower, then V counter is lower. So this is lower. The source voltage is fixed, so this is higher, right? We're subtracting a smaller number here from V sub S, and so we're going to get something that's higher for the net voltage across the armature. Okay, if the voltage across the armature is higher, then, so this is higher, then the current through the armature is higher. And if we have higher current through the armature, then the force, and thus the torque, on the armature, remember this equation from the equation sheet, this is the Lorentz force equation. If this current is higher, then this force is also higher. So the torque increases, all right? You didn't need to go through this entire chain of logic for your answer, but some indication that you had an idea of what was going on here is bound up in the why. Okay, last part, and then we'll cut it off there. What happens to the output of the generator, and why? All right, so we're assuming the mechanical input can handle whatever we're throwing at it, so that just the rotor whirs along at whatever speed, and so we don't have to worry about that part of it. We just focus on the electrical bits. Okay, now the thing to remember is that the field windings are in parallel with the armature in this generator, okay? So that is a situation that we had in an assignment question, if you go back a couple of assignments, and we answered, I think, almost exactly the same question in that situation, though phrased a little bit differently, okay? But if the torque increases in this part of the question, remember that means that the current is higher in the motor, okay? That means that the generator must supply more power, right? Because if current is higher, then generally speaking, the power is also going to be higher, right? Generator must supply more current would also be a perfectly reasonable thing to say, okay? And you might think, oh, well, then the voltage has to drop or the voltage has to go up, but, okay, so more power, so that means total current must increase, right? Because more current must flow from the generator to the motor because of what we discussed up here in the first part of this little part of the problem. And that, right, total I must increase. We might look back at our equations for the generator. We might say, oh, well, if that increases, then the voltage increases because the magnetic field is going to change. But remember, the field windings here are in parallel. Their resistance doesn't change, okay? So the I through field windings, though, is constant. So the V out from the generator remains constant. Okay. It's a nice feature of these so-called parallel wound or shunt wound generators, is that their output, no matter what the load, is pretty constant. Technically, the armature windings in the generator do have some resistance, so if you're increasing the total current, then the current through those armature windings is increasing, so you're going to drop a little bit of voltage from the output across those armature windings, so there'll be a small decrease in the voltage output, but we didn't really get into that kind of detail, and so you're not clearly not responsible for it here, okay? So that's what we covered on the assignment, and that's what we were asked about here, and that's the end of question 1. We'll come back with questions probably 2 and 3 in the second video.